As programming languages evolve, the trend always seems to be adding stuff. More abstractions, more libraries, more syntactic sugar. But what if I wanted to go the other way? What if I wanted Dijkstra to start rolling in his grave fast enough it could power a small nation? What if I decided to make a language where the only control instruction was GOTO? No loops, no functions, no structured control flow, just labels and jumps. Even assembly is more complex than this, so what can you realistically do without all the features that make modern languages modern? And languages. Well, prepare to have your curiosity sated as I am about to show you what a GOTO only language can do. Oh, and if you find yourself enjoying my casual stroll into insanity, consider liking and subscribing. Of course, before doing stuff in the GOTO lang, I actually need to implement the infrastructure for using the language, aka creating an interpreter. Conceptually, the interpreter is split into three parts: a lexer, a parser, and an execution engine. The lexer is the simplest component. Its job is just to read the source code and break it into tokens. Tokens are things like identifiers, numbers, or strings. For example, if the source code contains a line like add AB, the lexer simply produces a list of all the tokens identified. It doesn't try to understand what those tokens mean yet. It just splits things up so that the next stage can make sense of them. The parser is where the tokens start turning into something meaningful. Instead of strings like add and set, the parser converts each instruction into a structured representation. So, instead of raw text, the interpreter ends up with a list of instructions that are easy to execute. One thing the parser also handles is labels. Whenever the parser sees something like label loop, it records the position of that instruction. And later, if a GOTO loop appears, the interpreter already knows exactly where to jump. This is important because it means the interpreter doesn't have to search for labels while running the program. Everything is resolved ahead of time. Once the instructions are parsed, the interpreter itself is a walk in the park. Execution revolves around a program counter, which is just an index into the instruction list. The interpreter repeatedly executes instructions like this. Most instructions simply move the counter forward, but instructions like GOTO replace the counter with a different position. And that's the entire control flow system. No call stack, no recursion, no functions. Just a pointer moving through a list of instructions. And with this, the entirety of GOTO lang is as follows. You have 11 instructions, which can be grouped like this. You have control flow instructions, data instructions, and I/O instructions. And you might say, well, that's not a GOTO only language then, is it? And first of all, fair. But also, I think you also expect some programming to take place here, right? Well, in this form, GOTO lang is barely complex enough to qualify as a programming language. Sure, you could remove some more, for example halt, and assume the end of file as the end of the program. But you still need to be able to have variables, modify their values, and have conditional jumps. Unless you want the peak of your language's complexity be reading and printing the same value. Also, because this might not be as easily understood as I'd hope, the if statement is a bit of a special case, and it goes like this. First, you declare a logic instruction like EQ or LT and provide its operands. This instruction is then executed by the interpreter, and the Boolean result is kept as a flag in memory to be used by the next available if statement. The if statement is just a label to which the program will jump if that flag I mentioned is set to true. Otherwise, no jump takes place. Okay, so the interpreter is working. I even got it warmed up by trying out some really simple examples. Oh, and also we have proper error reporting and linting. Present me is thankful for the time I took to figure this one out. But now it's time for the big boy toys. Time to write some real programs in it. And almost instantly I got hit with the cold, hard, uncomfortable truth. There are no arrays, there are no loops, and there is no indirect addressing. If I want to store 10 numbers, I gotta write 10 variables. If I want a loop, I have to manually build one using jumps. And not saying that this makes writing programs impossible, just that it made me realize I was in for a real fun time. Fun for you, dear viewer, and current me looking back on how stupid I was. Let's start with everyone's favorite before bed ASMR routine, sorting algorithms. bubbly ones. In simple terms, bubble sort repeatedly walks through a list and swaps adjacent elements if they're in the wrong order. So, if you start with something like this, the algorithm compares neighbors sequentially, and after one pass, the largest value has bubbled to the end. Then the process repeats until the list is sorted. In a normal language, you'd write something like this. However, in a language where only GOTOs exist, a loop turns into a series of jumps and labels, like this, and each comparison looks like this. Also, swapping requires a temporary variable. All pretty straightforward till this point. Unfortunately, it gets even more straightforward, as there aren't any arrays, so I gotta use my own very hand to explicitly write out every comparison step instead of iterating through indices like a normal person does. So the program ends up containing sequences like this. Well, with sorting algorithms conquered, loops and control operations rendered useless, time to move on to the next logical evolutionary step, creating an interpreter inside my newly created interpreted language. And why stop there? Why not do it for one if not the most confusing language there is? Brain. You've probably heard of brain before, but if you haven't, here's a quick rundown. It only has these 8 instructions. Using these, brain programs operate on a tape of memory cells and a pointer that moves along the tape. Imagine a long row of boxes. The plus instruction increments the value in the current cell. The greater than instruction moves the pointer to the right. This way, a tiny program like this means first increase the first cell 3 times, then move the pointer right, and last increase the second cell twice. So the tape becomes now this. Loops are handled using open and closed square brackets. A classic brainfuck loop looks like this. This loop moves a value from one cell to the next. It says, while current cell isn't 0, decrement it. Move right, increment, and move left. When the loop ends, the value has been transferred. Okay, explanation over. Time to implement its interpreter in my very own GOTO lang. Basically, I need to simulate the tape, the data pointer, and the instruction pointer. The tape becomes a fixed set of variables. The pointer is stored in a variable called something like PTR. The tricky part is accessing the current cell. Normally, you'd write something like this, but that's impossible here. Instead, the interpreter checks the pointer value and jumps to the correct variable. Every cell access pretty much becomes a small decision tree. Now, loops. And take into consideration the fact I don't even have them in the language I am using to interpret this. When brain is an open square bracket instruction, it must jump to the matching closed square bracket if the current cell is 0. So, interpreter inside interpreter done. Time to test it out. I wrote, to add to my increasing despair, a few programs in brain. I started off with a simple one, printing a number. For this, the BF program looks like this, which means that the current cell is incremented 5 times and then printed. As a limitation of the GOTO lang, all inputs are numbers, so I had to adapt both the interpreter and the programs to be numbers only. So, using this table of equivalencies, the BF program looks like this. And as you can see, the program prints 5, as expected. Next, I wanted to swap 2 numbers. The BF code looks like this, which translates to read num1 into cell 1, shift right, read num2 into cell 2, print num2 from cell 2, shift left, print num1 from cell 1. And finally, a loop. This one is a bit trickier than the others, and it goes like this. First, increment the first cell twice. Then the loop is, as long as cell 1 isn't 0, shift right, increment current cell, aka the second one, shift left, and decrement current cell, aka the first one. After 2 passes, the first cell is 0, the loop stops, then it shifts to the second cell and finally prints the current cell. And in case you missed it, all this effort was just to move a value from one cell to the next. And the program prints 2, which is what I expected to see. That being the value of the second cell. From here, I thought I'd try my hand at some simulations. A cellular automaton is essentially a grid where each cell updates based on its neighbors. A famous example is Conway's Game of Life. Each cell checks the 8 cells around it and decides whether it lives or dies in the next generation. How would you do this without arrays or loops, you ask? So did I. Let's take a small grid that looks something like this. Updating a single cell means summing its neighbors. For example, the cell at C11 might compute as this. My GOTO lang take on Conway's Game of Life is within a 4x4 grid with wrapping edges. meaning the top edge sees the bottom row as neighbors, left edge sees the right column as neighbors, and so on. The grid is stored as 16 variables, one for each cell. The main generation loop repeats until the steps variable reaches 0, and that loop is run for the number of generations I input. A dead cell is 0 printed as dot, whereas a live cell, meaning non-zero, is printed as hashtag, or pound for you old heads. To calculate the value of each cell, I have to manually sum each of its 8 neighbors. The rules themselves are written directly in jumps. The simulation also needs a second grid to store the next generation so that updates don't interfere with each other mid-step. So the updates are written to this second pseudo-grid, and after the current generation is complete, the main grid is updated and the frame is printed to standard output. And here's the stitching of all the generated frames for a full simulation. And for the peak of unpaid labor activities, creating a falling sand simulator using only GOTOs. This one uses a 10x10 grid with 3 materials. You have an empty cell, a sand cell, or a wall cell. Each step applies a simple rule set. If the space below sand is empty, move down. Otherwise, try it down left. Otherwise, try it down right. Again, the grid becomes a set of variables, and updating it means moving movement logic for each cell, each of the 100 individual cells, for each individual type, for each individual rule. Kind of about here is the moment where I realized it's time to stop. Safe to say I took the mentally sane option of not doing that, but I didn't simply chicken out of doing the simulation. I still want to see how this thing would look like purely in my GOTO lang. I'll just use a little helper to generate the boilerplate. The generator is written in Rust. Instead of writing logic for each grid cell manually, the generator loops over coordinates and emits the correct instructions. Conceptually, it does something like this, which produces the fully expanded program that the interpreter can run. Now, before I show you the finished product, and also get to run it, I just want to point something out. I now have a minimal language, programs written in that language, and a generator that expands higher level patterns into raw instructions, which is basically what compilers do. Modern languages work the same way. You write this, and the compiler expands that into lower level control flows. I'm just doing that expansion earlier in the pipeline, and technically the generator itself could be written in the GOTO language, which would make the language able to generate programs for itself. But let's not take it too far, or at least farther than it already is. But without further ado, here's a sand sim running in my very own GOTO lang, and a stitched up view for the fans. Well, I think I have managed to show that a programming language that is as simple as having only GOTOs as its main control instruction can still throw its hat into the ring of modern languages, with the only added cost of the sanity and health of its users. Now I'll just wait for someone willing to do something like a game engine or real-time simulations to better drive the point home.